Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help support us on Patreon if you can. And don't forget we have Academy-themed gear in the Academy store. Today we are going to discuss the potential of a new rocket system, the Vulcan-Centaur rocket system by the United Launch Alliance. The Vulcan rocket is 200 feet tall and 18 feet in diameter. That's 61.1 by 5.4 meters for the rest of the world. This is not as tall as the SpaceX Falcon 9, which is 70 meters tall, but it is wider. This gives Vulcan a higher volume than the Falcon 9. The Falcon 9 uses RP-1 for fuel and liquid oxygen for an oxidizer. The Vulcan uses liquid methane and liquid oxygen on the first stage, then liquid hydrogen and liquid oxygen on the Centaur second stage. There will also be the option to add solid rocket propellant boosters to the Vulcan. It can have 0, 2, 4, or 6 of these. Each SRB can produce a little more than 2,200 kilonewtons of force. Burning hydroxyl-terminated polybutadiene that works as a binder and fuel, combined with ammonium perchlorate as an oxidizer, and powdered aluminum both as fuel and to help retain and concentrate heat. This propellant burns through a GEM-63XL rocket motor. GEM stands for Graphite Epoxy Motor. Graphite epoxy is the lightweight composite used for the booster structure. You can learn more about aerospace composites in this lesson. If you don't mind my saying millimeters instead of micrometers at one point. Have to keep you all on your toes. It is traditional, by the way, to call a solid rocket system a motor rather than an engine. The GEM-63XL was developed by Northrop Grumman and is an extended version of the older GEM-63, first developed by Orbital ATK. The GEM-63XL is currently the world's largest single-piece solid rocket motor. It will be 22 meters long and 1.61 meters in diameter. This makes it taller and wider than a Rocket Lab Electron rocket. Each booster will have a propellant mass of 48,000 kilograms. And will burn all of this in the first 84 seconds of flight. We can divide the propellant mass by the burn time, 48,000 kilograms divided by 84 seconds, to get a propellant mass flow of 571 kilograms per second. But this is the average propellant flow. As a solid rocket motor burns, the geometry of the thrust core changes. This geometry can be designed to create a high thrust start and a low thrust finish, to keep the rocket from experiencing too much G-force. We can find the maximum propellant mass flow if we want to. We know that we can convert specific impulse to exhaust velocity. The specific impulse of the booster is given as 280 seconds. In vacuum, a specific impulse of 280 seconds multiplied by the force of gravity on Earth, 9.807 meters per second squared, gives us an exhaust velocity of 2,746 meters per second. The maximum thrust of the GEM-63XL was given as 2,200 kilonewtons. We know that thrust equals exhaust velocity times mass propellant flow, and we can switch that around to mass propellant flow equals thrust divided by exhaust velocity. That would be 2,200,000 newtons divided by 2,746 meters per second, giving us a maximum mass propellant flow of about 800 kilograms per second. Now we move to the first stage. The first stage of the Vulcan rocket is 5.4 meters or 18 feet in diameter, and 33 meters long, which is 109 feet. It was designed with technology evolved from the Atlas V and Delta IV rockets. The first stage is planned to burn liquid methane and liquid oxygen through a Blue Origin BE-4. Development of the Vulcan rocket system has been delayed by Blue Origin failing to produce a flight-worthy BE-4 on time. You can review the BE-4 and our theory on the cause of the delay in this lesson. ULA had considered the Aerojet Rocketdyne AR-1 instead of the BE-4. But the AR-1 does not use methane. It burns RP-1 instead. The AR-1 produces 2,200 kilonewtons of thrust, a little less than the 2,400 kilonewtons of the BE-4. The BE-4 was chosen instead, and Rocketdyne was negotiating with Firefly Aerospace to use the AR-1 on their planned beta launcher. You can learn more about Firefly in this lesson. The current Firefly website page for the beta shows it using 5 Reaver 2 rocket engines instead. Rocketdyne had spent nearly $86 million on the AR-1, and the U.S. Air Force had spent $295 million. The AR-1 is an oxygen-rich staged combustion engine, like the RD-180 and the BE-4. It does, in fact, look a lot like the RD-180, with 2 combustion chambers and 2 nozzles per turbopump. Looking back to the Vulcan first stage, these tanks are made from orthogrid aluminum barrels and spun-formed aluminum domes. Orthogrids are created by creating a thicker sheet of aluminum, then milling away everything except grid supports in the thinner wall. Spun-formed aluminum is where a metal disc is attached to a motor, then spun at high speed while tools help shape the final product. You can learn more about aluminum alloys in this lesson. These tanks will hold the liquid oxygen and liquid methane, which will be fed into the 2 BE-4 engines. The BE-4 is not powerful enough for 2 of them to effectively lift this rocket with such mass. This is why the GEM-63XL boosters will be necessary for most payloads. The second stage of the Vulcan rocket will be an RL-10-powered Centaur system. This is one of the most efficient and capable second-stage systems in operation. The Centaur is also 5.4 meters in diameter, which is 18 feet, and 11.7 meters tall, 38.5 feet. It can hold a little more than 54,500 kilograms of liquid oxygen and liquid hydrogen. These are separated by a common dome, made of 2 domes of thin steel, separated by a fiberglass honeycomb insulator. The cryogenic liquid oxygen and hydrogen will burn through the most efficient rocket engines in existence today. The RL-10 has been perfected over decades. The RL-10 was the first liquid hydrogen rocket engine built in the United States. It was first built by Pratt & Whitney at the Marshall Space Flight Center in the 1950s, and first launched in 1963, in a 2-engine configuration as the second stage of an Atlas rocket. These were RL-10A3 versions. The Saturn I medium-lift rocket used 6 of these engines, and the McDonnell Douglas DCX, described in this lesson, used 4 of them. The RL series are expander cycle engines that produce 110 kilonewtons of thrust and can be throttled down to very low levels. An RL-10 version, called the Common Extensible Cryogenic Engine, was able to throttle down to only 6% full thrust. The Vulcan will use the RL-10C version, upgrading to an RL-10CX, which will have nozzle extensions when development is completed. Interestingly, the Centaur second stage is made of 301 stainless steel, just like the Starship. If you want to learn more about steel alloys, we have this lesson. The RL-10C21 Hydrolox rocket engine has a specific impulse of 465.5 seconds. That is the best it gets for chemical rockets so far. A bright scholar asked me about octa-oxygen recently. I would like to say I knew all about it, but I did not. I'm reading up on it, and we'll look at the potential of an octa-oxygen and metallic hydrogen rocket. Until then, the RL-10C21 is the master of chemical rocket engine efficiency. The Vulcan-Centaur second stage will use the 454-second specific impulse RL-10 version, sacrificing a little efficiency for increased thrust. We can convert the specific impulse to exhaust velocity. 454 times 9.807 equals 4,565 meters per second. The Vulcan-Centaur second stage will be the larger Centaur 5 version. The average Centaur second stage only holds a little less than 21,000 kilograms of propellant and has a dry mass of 2,462 kilograms in the 2-engine configuration. I can't find the dry mass of the larger Centaur 5, but I did find a liftoff mass of 59,800 kilograms. It's underweight, but that's a common mistake Americans make. Here it lists the propellant weight of 6 GEM-63XL boosters as 288 tons. If we divide 288 by 6, we get 48,000, listed by ULA as the SRB's mass. So here they are listing metric tons of mass instead of imperial tons of weight. If we subtract the 54,000 kilograms of propellant from the 59,800 kilogram wet mass means loaded with propellants, we get a dry mass of 5,800 kilograms. If we put one of these on the ground with no payload and launched it on its own, we would get a delta V of delta V equals exhaust velocity times the natural log of initial mass over final mass, and we get a delta V of 10,388 meters per second, which is 10.4 kilometers per second. We might think that means a Centaur second stage would be a single stage to orbit vehicle, but a mass of 59,800 kilograms gives us a weight of 586,459 newtons. Each RL-10C engine has a thrust of about 100,000 newtons. 2 of them won't get this off the ground. It would take at least 6 of them to barely get going. Each engine has a mass of about 230 kilograms. Adding 4 of them increases our mass by 920 kilograms, which is 9,022 newtons. That brings our launch weight to 595,481 newtons. Using just 6 engines would give us a thrust-to-weight ratio of 1.008. This thing would climb like that poor Astro rocket we saw, that lost 1 engine immediately at launch. We would need at least 9 RL-10 engines total to get a decent thrust-to-weight ratio of 1.49. But now we've changed our dry mass from 5,800 kilograms to 6,410 kilograms. Now our delta V goes from 10.4 kilometers per second to 9.42 kilometers per second. This thing could still lift itself to orbit, but just barely, and with no payload, as it takes 9.4 kilometers per second to give us the minimum stable orbital velocity of 7.8 kilometers per second. We go through these exercises to show that changing anything on a rocket changes everything else. The Vulcan rocket can also be built in a Vulcan-Centaur heavy configuration. This will have 6 SRB boosters and the new RL-10CX engines with nozzle extensions. This rocket will be able to get 27.2 metric tons to low Earth orbit, and 26,200 up to the ISS, 14,400 to geosynchronous transfer orbit. That means it's thrown out to geosynchronous distance, and then the engines fire again to circularize the orbit. And finally, 12.1 tons to a translunar injection orbit. If this rocket has a chance to fly, it will be a very capable system, but it will be expendable. A Falcon 9, if the first stage booster is expended and not recovered, can get 22,800 kilograms to low Earth orbit, beating the Vulcan-Centaur. The Vulcan-Centaur will cost between $82 and $200 million per flight. As of 2022, the Falcon 9 was flying at $67 million. A non-reusable Falcon Heavy would have a cost of $150 million and a reusable one of $90 million, and can get up to 68,000 kilograms to low Earth orbit. I don't know why ULA is working so hard to build something that can't compete with what's already on the market. Why doesn't anyone plan to build something bigger than Starship? We'll discuss that possibility in an upcoming lesson. Until then, thanks for listening, and stay safe at Astra Pro Terra.